Welcome back. Good. So we looked at the canonical ensemble, and we looked at a two-level system, right? So we want to look at some other models, application of canonical formalism to the model of paramagnetism, right? And our model Hamiltonian is sum over minus mu I dot h, I is equal to 1 to n, where mu I is the magnetic moment on the ith side and h is the magnetic field which has been applied externally. So the thing is that I have this spin sitting on the lattice, except that they are no longer plus 1 minus 1, but they can rotate freely on this circle of radius given by the modulus of this. So therefore, you see the configuration of this rotor or this spin with the angle theta is the one which essentially describes the microstate of the system, and the partition function is given by sum over all states e to the power minus beta mu I h dot h sum over I. The single particle partition function, this is where the n particle partition function is. The single particle partition function is sum over all states e to the power minus beta mu I dot h, right? And since it can rotate in a circle, so that we can write down as 0 to 2 pi minus 1 to plus 1 d of cosine theta e to the power minus beta mu h cos theta. The integral is very easy to do, so one recovers 4 pi by beta mu h sine hyperbolic beta mu h if you do the integral, right? The n particle partition function z of n is e to the power, is q to the power n, which is equal to 4 pi beta mu h sine hyperbolic beta mu h, and this is being raised to the power n. Note that here I have not used an n factorial in the denominator because I assume that the particles are distinguishable by their lattice points. The free energy is minus kBt ln of Zn, which in this case becomes minus n kBt ln sine hyperbolic beta mu h minus ln beta mu h plus ln of 4 pi. It's not very significant for us, it's because it's just a constant number. Good. That with the free energy F from the partition n particle partition function, we would like to proceed further. But there is a word of caution over here. Now, if you identify this with the Helmholtz free energy, even though I have written notation F, if you identify this with the Helmholtz free energy, you will be in trouble, because you see when we did the Helmholtz free energy, that thermodynamic potential was defined in the presence of no mechanical work. On the other hand, the Gibbs free energy was defined in the presence of a constant mechanical constant conjugate force. And if you look at the Hamiltonian over here, you see that the magnetic field has already been applied over here. So there is a presence of a constant magnetic field. So in fact, therefore, the legendary transformation that you are looking for is just not this, but h times m. So df is du minus tds minus sdt minus hdm minus mdh. Du minus tds minus mdh is the first law. Sorry, not minus mdh. I beg your pardon. It's minus hdm, which forms the first law. Right? And therefore this is 0. So what you are left out with is minus sdt minus mdh. And it follows, therefore, the magnetization is del F del H, temperature constant. So m is minus del F del H, temperature constant, and this is the equation of state. So let's see, this is going to be nkBT. Del H of the first term, which is this one, is going to give you sine hyperbolic beta mu H times cos hyperbolic beta mu H times beta mu minus 1 over beta mu H times beta mu. Once the beta mu come outside, you can immediately see that this is going to be n mu. This is cot hyperbolic beta mu H minus 1 by beta mu H. So which we write down as n mu L of x, where x is equal to beta mu H. And this function is called the Langevin function. As x tends to infinity, L of x approaches unity. And this tends to infinity means that the temperature tends to 0, so that beta tends to infinity. So at very low temperatures, you find that the magnetization is equal to, the magnetization tends to the limit n times mu. All of them are pointed along the same direction. There are not enough thermal fluctuation or thermal energy in the system to make them fluctuate, right? The fluctuations are suppressed. As x tends to 0, Lx is approximately x over 3. So therefore, magnetization is n times mu. One can just do it. X is mu H over 3 kBT, right? So that this is approximately n times mu square H times 3 kBT. And the susceptibility is del M del H at constant temperature, which is chi of T, and which you get as n mu square over 3 kBT. So your susceptibility, x tends to 0, means beta mu H tends to 0, which means T tends to infinity, which means you have a large temperature, so that your fluctuations are more. So you can imagine that this rotation of this is more as opposed to a low temperature, and this goes as 1 by T. This is what is called Curie's law of paramagnetism. Now what about the quantum mechanical analog of the same problem, where I have the same Hamiltonian, but there are several changes one has to realize. That the magnetic moment, if J is a spin, then the magnetic moment is, is mu naught times J, where mu naught is given by, is a product of two terms. One is the Landau factor, which is G, and then it is EH bar by 2mc, right? So this is where we are looking for the quantum mechanical treatment of the same problem. So J is the spin of the particle. Therefore, this means that the magnetic moment of the particle is given by mu naught times J, where mu naught is this quantity. Without loss of generality, we take the magnetic field, we take H in the direction, or let's say in the Z direction, right? In this case, the Z component of the moment cannot be arbitrary, and it has eigenvalues mj, where mj now runs from minus j to plus j. This all of you would have done in quantum mechanics. So the single particle partition function is now sum over mj minus j to plus j e to the power minus beta mu naught h mj, right? Sorry, it a plus, and yeah, this also has to be plus in the classical limit, which is now one has to just write down the whole terms. So it runs from beta mu naught h j plus beta mu naught h j minus 1, so on and so forth, to e to the power minus beta mu naught h m times j. So now we can take e to the power beta mu naught h j common, and the series is going to be minus beta mu naught h plus e to the power minus 2 beta mu naught h, so on and so forth, ending up to e to the power minus 2 beta mu naught h j. So sorry, there is not going to be an m here. This series can be very easily summed, and you will have beta mu naught h j 1 minus e to the power minus beta mu naught h 2j plus 1 divided by 1 minus beta mu naught h by 2, right? So which becomes, with a little bit more simplification, if you manipulate this, this becomes sine hyperbolic beta mu naught h times j plus half divided by sine hyperbolic beta mu naught h by 2. This is your single particle partition function. Once you have the single particle partition function, the n particle partition function is given by q to the power n, which becomes sine hyperbolic beta mu naught h j plus half divided by sine hyperbolic beta mu naught h by 2 raised to the power n. Free energy is minus kBt ln of Zn, which you have as n kBt minus, you will have ln of sine hyperbolic, we will call beta mu naught h as equal to x, so that j plus half times x minus ln sine hyperbolic x by 2. The equation of state, which is del f del h with a minus sign, temperature held constant, is the magnetization m, gives me n times kBt. The first term is going to give me cot hyperbolic j plus half times x multiplied by j plus half times del x del h. The second term is going to give me cot x by 2 times half del x del h. which is nkbt cot hyperbolic j plus half times x times j plus half del x del h is beta mu naught times beta mu naught minus beta mu naught by 2 cot hyperbolic x by 2. Good, let's simplify. Let's take the beta mu naught outside so that I have n times mu naught j to j plus 1 by 2 cot hyperbolic 2j plus 1 by 2 times x minus 1 by 2 cot hyperbolic x by 2. So this we define as n times mu naught times j times bj of x, where your bj of x is 2j plus 1 by 2j cot hyperbolic 2j plus 1 by 2 times x minus 1 over 2j cot hyperbolic x by 2. And this function is what is called a Below function. If you take a large value of j in the limit of large j, in the limit of large j, this function will go to the Langevin function L of x, which we have seen earlier.